So now what we're going to talk about is significant figures. And this is what resolution really builds up to. Knowing how many numbers to write down when you make a measurement tells you how many numbers to keep when you make a calculation using that measurement. And so that's what we're going to talk about with regards to significant figures. But first we have to define what a significant figure is. It is any non-zero digit. That means any number 1 through 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 counts as a significant digit or a significant figure. If you have a sandwich zero, that means it's stuck in between two non-zero digits. It can be 2 of them in a row, it can be 8 of them in a row. It doesn't even really matter. But what it tells you is that somebody, when they made this measurement, this is their uncertain number. They are absolutely certain about the first 4. So that's why you keep it. It's because that last digit is the uncertain one. That's the one where the resolution kicks in. If you have a trailing zero, what that means is it is a zero that follows behind a non-zero number. So 30. It counts, and this is by convention, it counts only if you see a decimal point present. So if I have 30 like this, that only has one significant figure. That zero is an estimate. They're not real sure about it. It could be 29, could be 28, could be 32. It's been estimated. 30 with a decimal tells you that they're fairly certain about that zero, that it's somewhere in between 30 and 31, but they don't know exactly what. So that's the convention we use. If you actually see a decimal point, the zero that trails behind a non-zero digit counts. Okay? If I had 30, both of those zeros with a decimal point in between trail behind the number 3, the non-zero digit. They count as significant since there is a decimal point drawn. If you have any digit that is a multiplier of a number in scientific notation, so if I had this number, the 3, the 7, and the 5 are non-zero digits, the 0 that trails behind the 5 counts as a significant digit because of this rule number 3, because there is a decimal point present. Okay, the easiest way to deal with this is if it's in correct scientific notation, every single number that's written here is significant if it's been written correctly. The multiplier part of it, the magnitude part of it, doesn't count. All it is moving the decimal point. Sig figs are also infinite if it's any kind of a counting number. So for example, if I'm counting how many pencils I have, 12. I'm making a measurement. I'm observing how many pencils I have. However, there's no ambiguity. It's not like I can have, 12.25 pencils. I have 12 pencils, or I have 13, or I have 11. It's not vague. Okay, and then conversion factors. When you're talking metric system or in the English system, they have infinite sig figs because it's by definition. Okay, the one thing that doesn't count for sig figs is anytime you have a leading zero. That means written to the left of a non-zero digit. All of these zeros right here are leading zeros. All they are is placeholders. They're not significant. The only ones that are significant are the 3 and the 5 for being non-zero digits, and the 0 that trails behind the 5 because there is a decimal point present somewhere in the problem. So let's practice some of these, and we'll underline all the sig figs. So if I have this measurement, the 2, the 7, and the 8 are all significant because they're non-zero digits. The 0 trails behind the 8, and there is a decimal point. It has 4 sig figs. This number, the 3, is a non-zero digit, so there's 1. These 2 zeros here are also significant because they trail behind the number 3, and there's a decimal point. Those do not count as significant. They're important because they're placeholders, but they're not important in terms of making the measurement. So this would have 3 sig figs. Okay. This one is a number in scientific notation, so all 3 of those non-zero digits count. We'll go back. This one, the 8 counts. These 3 zeros are what's called trailing zeros, but there is no decimal point drawn. Because there's no decimal point drawn, it is a 1 significant figure. Those zeros are only placeholders. Okay, there's clearly a difference between 8 and 8,000. But the 1,000 part of it is just a multiplier. It's a magnitude. Okay. This one, the 4, the 7, and the 3 are non-zero digits. The first 0 and the second 0 are called sandwiched. They're between two non-zero digits. And this last 0 is trailing behind the 3, and there is a decimal point. It means it has 6 sig figs. This one, the non-zero digit 4, counts. These zeros are leading zeros. They lead up to a non-zero digit. There is only 1 sig fig. And then 25 pencils is infinite because it's a measuring. And then 12 inches, 1 foot by definition. Okay, now when it comes to using sig figs in calculations, so we are going to be doing a lot of calculations this year. The way it works for sig figs is anytime you make a measurement and you have some uncertainty associated with that measurement, you have to carry that uncertainty through anytime you're making calculations. For example, if you're uncertain on the length of a table and you're uncertain on the width of a table, that uncertainty gets carried through when you calculate the area. And so there are rules for this, figuring out the calculations that involve measurements. So you need to pay attention to these rules. We're going to do them all year long, primarily in the lab, but also in practice problems. So the rule for multiplication and division. The number of sig figs in the final answer is based on the number with the fewest sig figs in the problem. So this is where you look at what your calculator says, and you round to the appropriate number of sig figs based on the number in the problem that has the least. Okay, so if I multiply that out of my calculator doesn't say 6.4. My calculator says 6.384, but this has 3 sig figs, that has 2. It means I have to round 6.384 to 2 sig figs. The 8 rounds up to 3, and that is the only acceptable answer for a measurement that involves a calculation, or a calculation that involves measurements. So if I do 18 divided by 123.6, I get 0.145631067961116. Now clearly I don't want you to write those numbers all down. We're going to use sig fig rules. Well, this number, the 1 and the 8 are non-zero digits, and the 0 is trailing behind the 8 with a decimal point. That has 3. This has 4. That means I'm going to take this and I'm going to round it to 3 sig figs. The 0 in the front is a leading 0. It's important to keep it, but it is not significant. It's a placeholder. So the 6 rounds up to 5, and I'm going to keep those numbers 0.146. Okay, the 0 to the left is a placeholder. If you want, one of the things that you can do that will always work is if you write it in correct scientific notation, you will always be right. Not -3. Let's try -1. You will always be correct. Scientific notation works every time. Now, if I multiply those two together, this has 3 sig figs, that has 1, my calculator will say this, but I'm only allowed to have 1 sig fig. That's why we try really hard not to have 1 sig fig. When you're making a measurement, the rounding that comes in really screws you up. So 3,900 has to be rounded to only 1 sig fig, so it becomes 4,000. You can't just call it 4. There's a difference between 4 and 4,000. That's a magnitude difference. But the sig figs are defined by the numbers in the problem. So if I had this one, I have 3 sig figs, I have 2 sig figs, I have 2 sig figs, it's all good. That one's okay. If I do this, I haven't changed the number, the magnitude of it hasn't changed. The number itself, the multiplication has not changed. But when I have 3 sig figs and 3 sig figs, I have to have 3 sig figs. So I can't write 390, because there's a difference between 390 and 3,900. I can't write 3,900 and put the decimal point there, because that gives me 4 sig figs. I'm only allowed 3. So the only way to get this to work is to put it into scientific notation, because that will work every time. Okay, addition and subtraction is a little bit harder. The final answer in any addition and subtraction will have the same number of sig figs to the right of the decimal point as the number in the problem with the fewest to the right of the decimal point. So you're always going with the least. Multiplication is the least overall, division's least overall. Addition and subtraction are the least passed to the right of the decimal point. So if I add those all together, all I'm looking at is this number, this one, and this one. 2 to the right of the decimal, 1 to the right of the decimal, and 3. That means my answer can only have 1 to the right of the decimal. If I do something like this, 1 to the right, 2 to the right, I'm only allowed to have 1 to the right of the decimal. And then here, this doesn't have any past the decimal point. That means I can't have any. So even though my calculator says 213.85, I have to round it so that I don't have anything after the decimal point. Well, it's like I almost didn't subtract it at all. That's why you really want to make sure you have the correct number of sig figs to the right of a decimal point, particularly when you're doing stuff in the lab. Okay, so let's just practice these. I'm going to run them through on my calculator real quick. And my calculator says 5.21664 and 2.625 and 0.003978 49. I think that's enough. I'm not going to write everything else down. This is 5. 3.666. $119.45. All right, so now let's talk about sig figs. So this is just doing the math. When I look at this number, I see 3. This one has 4. That means my answer is only allowed to have 3. Well, that 6 rounds up the 1, and I keep the first 3, 5.22. This has 2 sig figs. That has 1. That means I only keep the first number. The 6 rounds it up. The answer is 3. That's why you want lots of sig figs. It tends to take away those rounding errors. Okay. This is all multiplication, so the rules are total number sig figs 2, 3, 1. I'm only allowed to keep 1. Those zeros I have to keep because they're placeholders. So I keep the first non-zero digit, the first significant digit that I run into, which is 4. Or you can put it in scientific notation. It will work every time, 4e negative 3. Okay, this number, again, division. 4 sig figs, 4 sig figs. Even though my calculator says 5, to be correct with sig figs, I need to stick those extra zeros in there. Numerically, it makes no difference. But in terms of sig figs, it makes a huge difference. Again, multiplying here, I see 2 sig figs, 2 sig figs, 3.7. Now, addition and subtraction are a little different. It's not the total number of sig figs. It's only the ones to the right of the decimal point. That has 1, that has 2. All right, so 1 sig fig, 2 sig figs, 1 sig fig. That means I'm only going to keep one number after the decimal point. The 5 rounds it up, it becomes 119.5. And then subtracting. This is fortunate. This is what you're going to see most of the time. You put something on a balance, it weighs 6.16. You add something to it to find out how much the thing weighs. You add to it, you subtract. But the balance builds in the sig figs for you. There are 2 here and 2 here. That means 2 here. Okay, these are the tricky ones, adding and subtracting. Multiplication's pretty easy, and you definitely get the hang of it after a while. Okay.